Hi, I'm Kit Shann, and this is Group 5's project presentation on seawater intrusion. We'll first lay out a background and problem statement, followed by variables and assumption, problem solution, analysis and model assessment of sea solution, and finally ending off with future considerations. Our focus area will be on rising sea levels. Since the 1880s, the average global temperature has increased by a staggering 1 degree Celsius, and is expected to increase by a further 1.5 degrees Celsius by 2050. This is mainly due to human intervention, a major factor being the burning of fossil fuels, which produce greenhouse gases that trap heat within the ozone layer and thus causing ice caps to melt due to the temperature rise, ultimately resulting in sea levels to rise. This brings different impacts such as damage of property, loss of lives, economic loss, and flooding, which brings us to our focus area, Miami, Florida, which is most at risk in terms of sea level rise. This is due to it being a low-lying coastal plain adjacent to the North Atlantic Ocean and its foundations made of porous limestone, which allows seawater to permeate and erode the bed, undermining structures below, and thus resulting in increased flood-related events. Not to mention, in 2022, the global mean sea level was over 100 millimeters of that it was in 1993, making it the highest annual average in the satellite record. So, what can we do about this? Well, for our problem statement, we wish to develop a supervised deep learning neural network model that can accurately predict future sea level rise in Miami, Florida.
Now, I will be covering the independent and dependent variables included in our model, as well as the assumptions made in both our data and model structure. The independent variables that we use are as follows. The local annual mean temperature of Miami in degrees Celsius, which acts as a proxy for global warming. The local annual mean atmospheric CO2 concentration in Miami in parts per million, which impacts the ocean acidity and temperature specifically around Miami. The local annual mean Miami precipitation in millimeters, which can deviate from the long-term average precipitation amount for Miami, and hence capture changes in rainfall that may affect local sea levels. And finally, the regional ice sheet and glacier extent in 10 to the power 6 square kilometers, which incorporates the changes in the amount of ice in the northern hemisphere. For our dependent variable, we measure the local annual mean sea level in the Miami in meters to see how all these independent variables lead to the rise in sea levels. For our data assumptions, we look at three main assumptions: the availability of historical data, which includes comprehensive and relevant data for the area surrounding Miami, the data quality, ensuring that our data is accurate, reliable, and has been measured over time, and finally, the temporal scope, where our data covers a sufficient period from 1979 to 2019 that captures both short-term variability and long-term trends. For our model assumptions, we look at causality over correlations, assuming that our selected variables have a causal relationship with sea level rise, and the form of neural networks, assuming that it can effectively capture complex non-linear relationships via its architecture. We also look at model predictability, assuming that future sea level rise can be estimated using our current data and extrapolation outside of our current data range, assuming predictions made slightly out of range are still valid despite risk of substantial errors and significant extrapolation. At the end of the day, while our data is reliable according to current day statistics, it is essential to regularly reassess these assumptions against the latest scientific findings and methods to make sure the model remains valid over time.
Thanks, Faustina. Now we move on the part of problem solution to dive into how we can model and analyzing the neural network to predict sea level rise. First, our solution we split into two parts. First part should be here is about data collection stage. The first step, we need to gather accurate and reliable dataset within aforementioned variable from our finding resources of meteorblue.com, calculate.com, sealevel.info. Second step that we filter our dataset from the raw dataset. That means we just keep and utilize some major dataset from aforementioned variable. The third step is about reassessing that we should have calculate and measure the mean value of four variable dataset throughout the 40 years period. Then the last step is to incorporate on our dataset into one comma separate value spreadsheet prepared for analyzing in the following test. Now we move on the main part of our problem solution is functional solution that we will model and we dig the result throughout our two hidden layers, and we can see that our model has four independent variables. We construct four of them as a vector of four input variable. Each of data of variable dataset will travel to all the layers, specifically to hidden layer. The first layer we construct will be calculated for n neuron inside the layer. For I we go from 1 to n neuron where WGI1 is the wave from input J to neuron 1, I in the hidden layer 1. This wave term is the connection between two basic units in our neural network. BI1, the bias term for our neuron I in the hidden layer 1. This bias value will help us to offset the result, which can assist in calculating the offset value between actual and predict result to analyze the model accuracy. A value, The activation function applied to each neuron. This A value will introduce the nonlinearity into the output of a neuron. Then our second hidden layer will include M neuron inside and will take the output from first hidden layer to measure the meaning of the weight and bias term at this second layer is similar to that of first hidden layer. After on hidden layer, our variable will go to the last layer called output layer to predict the result. Output layer helps us to calculate the offset value between actual and testing data for analyzing the model accuracy. The last output result will be utilized in various human purposes, from governmental checking for solution facing extreme weather. Specifically, the trending factor now is sea level rising. Then it also could be planting checking and sewer construction planning for coastal protection. Our model was honored to utilize the Python library, which support to analyze complex and large dataset. Python's allow library are training and testing our neural network model by Keras library and visualizing statistical graphic by Seaborn and Mathematic library.
Now we will be talking about our analysis and model assessment. The contour map analysis emphasizes the significance of annual mean temperature and atmospheric CO2 level as crucial model inputs for understanding and predicting sea level rise in Miami. The contours reveal the upward slope, indicating the projected rising sea level increases with higher temperatures and CO2 concentrations. The positive correlation between temperature and sea level rise is strong, with even minor temperature increases. Similarly, CO2 levels positively correlate with sea level rise, and the combined effect of temperature and CO2 intensify the impact at high levels. The steep slope on the temperature axis underscores the sensitivity of projections to small temperature changes. The non-linear shape of the contour reflects the complex interactions captured by the neural network model. In summary, the analysis validates the inclusion of temperature and CO2 concentration as model inputs due to their measurable global increases and clear linkage to sea level changes. The model loss graph describes a loss curve throughout training, starting at approximately 0.05 and decreasing rapidly in the initial 5 epochs, indicating a well-tuned initial learning rate. By epoch 10, the slope levels off as model converges, reaching a final loss of 0.0042, which is a sufficiently low value for a good fit. The smooth and consistent downward trend illustrates effective optimization and learning. Similarly, the model's mean absolute error graph shows promising characteristics. The MAE decreases from 0.29 to 0.008 on the training set, indicating a strong fit to the data. Notably, a minor gap between training and validation MAE with a final value at 0.033. This suggests there is no minor overfitting as the model generalizes effectively to new data.
Thank you, Yu Qing. We believe that our model does have its strengths and its weaknesses. Leveraging our understanding of climate change, we were able to integrate various climate variables to gain a comprehensive understanding of sea level rise. Through this, we believe our model surpasses human ability in crunching and processing large sets of data to identify non-linear relationships quickly and accurately. Furthermore, with our effective data visualization, government bodies with varying technical backgrounds can more readily and effectively understand our data, enabling them to formulate optimal adaptation strategies and timelines that suit the unique needs for their coastal communities. However, it's important to acknowledge our model's weaknesses. Due to the complexity of our neural network and the data set it's trained on, there's a risk of overfitting. Additionally, insufficient integration of data points or input types may compromise the accuracy of predictions with unseen data. Moving forward, we would like to address these weaknesses. Our future plans involve integrating regularization techniques into our neural network model. Techniques such as dropout, early stopping callbacks, cross-validation, and L1, L2 regularization will mitigate overfitting, resulting in more accurate predictions of sea level rise. There's a saying in the world of neural networks: this is the worst that this technology is going to be from here on out. Our model, trained on Miami's historical sea level changes and correlated climate variables, holds significant potential in assisting government bodies in predicting the impacts of sea level rise on coastal communities. By embracing technological advancements, we can further refine our predictions, enabling better preparedness for the uncertainties ahead. Thank you.